Good afternoon, everyone. Today we are going to graph a function, namely f of x is this quadratic, and we're going to graph the square root of this first function. And so if f of x is x squared plus 4x plus 3, g of x is defined to be the square root of f of x. Okay? So first of all, when we look at the x squared plus 4x plus 3 function, we can quickly graph this parabola by getting the roots. And so I'm going to write it in factored form as x plus 3 times x plus 1. And from your previous math courses, you know from this that we have our roots at -3, 0, and at -1 and 0. And so that means a root here and a root there as well. If we want, we can get the vertex. We can write this in vertex form by completing the square. So that's x plus 2 all squared. We'll be subtracting 4 outside to balance it out, and minus 4 plus 3 will mean we get to -1, and so that means we have a vertex at -2 and positive 1. Sorry, -1. At -2 and -1, which makes sense because that's right in the middle of the two roots, which is exactly what we would expect because of the symmetry of our parabola. Now, we have an a value of 1 in front of x squared, and so we know the pattern. Starting from the vertex, we can move over 1, up 1, over 2, up 4, and we can get a few points on our graph pretty quickly in that form. And so over 2, up 4 brings us here as well. We can go over 3, up 9 if we really wanted to, somewhere up here, but I'd say that's enough for now, so we can get a rough sketch of our parabola defined by f of x, like so. And now, to graph the function g of x, which is the square root of the original f of x, we know that since we're taking the square root, this is only going to be defined for positive and 0 values of f of x. Namely, it won't be defined for any negative values of f of x, because we know for a while now that we can never take the square root of negative values. So, looking at our graph, we see that between the two roots at -3 and -1, g of x will be undefined. It won't have any curve at all between the two roots, okay? So, we know that at 0 and at 1 in the y-coordinates, we get our invariant points. That's always going to be the case when y is equal to 0 and when y is equal to 1. Right, we've discussed that this is because the square root of 0 is 0 itself, and likewise, the square root of 1 is also 1 itself. That's how we get invariant points, i.e. points that don't change positions on the graph when we go from f of x onto the function g of x, okay? So, y is equal to 0 is exactly what we have at the roots, and so those are our first 2 points for g of x that we get for free. Those are our invariant points, okay? Then we also have invariant points always whenever y is equal to 1. And so we can get those around here. We'll find the x-coordinates of those points a little bit later on, but it still gives some structure to our g of x curve. And then after that, what I recommend doing is finding some nice points along the way that are easy to evaluate the square root of, right? Because f of x, that gives us the y-coordinates of the points on this parabola. And so g of x takes the square root of each of those y-coordinates, right? Those y-coordinates are defined by the function f of x. And so, for example, at this point here, when y is equal to 4, that's a nice point to use because the square root of 4 is 2. So just below it, we get a nice point on the square root function at this same x-coordinate, which we don't need to know exactly, but we know that the y-coordinate instead of 4 is now 2, the square root of 4, okay? And that's symmetrical, so we can do the same thing on the other side. We get a point roughly here at 4, and so we'll get a point roughly here at 2, just vertically stacked below, okay? Now, again, you know that whenever 0 is less than y is less than 1, that the square root of y is bigger than y itself, right? For any value between 0 and 1, the square root of that value is bigger than the value itself. And so you've seen this before, presumably, between the section of y being 0 and y being 1, we get this hook curvature where the square root function is above the original function. And same idea on both sides of the curve. We get the invariant points, which also act as points of intersection, right? They really work in the same way. We get our points of intersection when y is 0 and y is 1. And now we can extend from there. And so we get something like this. Get a nice hook and then it goes off something like that. Okay. I always tell my students that as we get further and further from the y-axis, i.e. as the x's get bigger in magnitude, x squared plus 4x plus 3 starts to behave a lot like just x squared as x gets really, really big, right? As x gets really, really big, x squared is so much bigger than 4x and 3 that it's really only x squared that dictates the shape of the curve. And so when we eventually take the square root of basically x squared, what is the square root of x squared? Well, that would be x, right? And you know what the line y is equal to x is. Y is equal to x, right, is just a diagonal line with a slope of 1. And that's why as x goes further and further out, this shape looks just like a line with a slope of 1. And the same idea on the other side, but with a negative slope of 1, okay? So this is our curve g of x. We have one branch of it going northeast and another branch of it going northwest. And that is our function g of x, the square root of f of x, okay? Now, we're asked to state the domain and range for both f and g of x. So the domain of f of x, that's easy enough. That's the set of x values where x can be any real number, right? There are no restrictions in x for a parabola. Its range is the vertex and above. And so the range of f of x will be the set of y values where y can be anything on the vertex and up. The vertex again was at -2, -1. And so our range is y can be greater than or anything greater than or equal to -1, like so. Now moving on to our square root function, g of x. G of x, let's write the domain of g of x would be the set of x values such that, now g of x, as we've discussed, is undefined between the two roots, between the values of -3 and -1, right? And so that means it is defined from -3 and to the left and from -1 and to the right. And so we can write this in set notation as x less than or equal to -3 or x greater than or equal to -1, okay? If you wanted to use interval notation, you could write -∞ all the way to -3, inclusive, union, inclusive, positive, -1 rather, comma, infinity, round brackets. Always round brackets around the infinities because we never actually get to that value. And finally, I'll write that a bit smaller. That's a bit messy to read. Domain of our function g of x. There we go. And finally, the range of our square root function g of x will be the set of y values 0 and up, right? We do get a y value of 0 on the x-intercepts, and g of x goes up forever. And so y can be any value greater than or equal to 0. Again, if you'd rather interval notation, y can be on the interval 0 inclusive all the way through to positive infinity. And last, we were asked to state any invariant points from the function f of x onto the square root function g of x. And so those happen to be the points of intersection, or perhaps a bit more readily available. They are the points where the y-coordinates are 0 or 1. That's always going to be the case when we're looking at a function and the square root of said function. And so to find those points, we already have two of them. When y is equal to 0, those are the roots of f of x. And so those are the points -3, 0, -1, 0. And then we have the other 2 points where y is equal to 1, right? We've made mention of them because we drew them on the graph where they had a y-coordinate of 1, right? But we don't exactly know the x-coordinates, right? And so to find those, we need to plug in a value of 1 in for y. Y takes on a value of 1. And you know that whenever you have a function, f of x is equal to whatever that function might be, you know that f of x provides you with the y-coordinate of that function. Y is a function of the x variable, right? The y-coordinate is a function of the x-coordinate. And so if we know that y is equal to 1, then we can plug in a value of 1 in for f of x, and we can solve for x. And so let's go ahead and do that. 1 is equal to x squared plus 4x plus 3. Okay, and now we have to solve this equation in the same way that we've always solved our quadratic equations. Let's set one side equal to 0. X squared plus 4x now plus 2. This is not factorable, so we'll have to use the quadratic formula. Unfortunate, but that's okay. Plus or minus the square root of b squared. That's 16 minus 4ac minus 4 times 1 times 2 all over 2. And so x is -4 plus or minus, that's going to be the square root of 8. And the square root of 8 is 2 root 2, right? The square root of 8 is the square root of 4 times the square root of 2, which simplifies as 2 root 2. 16 minus 8 is 4. Square root of 8 is, again, 2 root 2. And this is all over 2, right? 2 times a, but a is 1. And now dividing both terms in the numerator by 2, we get our 2x values to be x is -2 plus or minus root 2. And we get a positive or a negative version of root 2, providing us with both of our invariant points with a y-coordinate of 1. And so the first one will have -2 minus root 2, -2 minus root 2, comma, positive 1. And the other invariant point will be at -2 plus root 2, comma, positive 1. And that concludes our solution, okay? I'll box this off because this was just to show a tiny bit of explanation as to how we found the x-coordinates of our invariant points. So we've successfully graphed a function and its square root function. We've stated domain and range for both. And we found any invariant points, i.e. any points of intersection between those two curves. I really hope this helps. If you guys have any questions, comments, or suggestions, please leave a message down below. And thanks for watching.